In this lecture, we're going to talk about computer arithmetic. We're going to go into some more detail than we did in the first lecture. So today we're going to cover binary numbers, talked about that a little bit before, addition and carries, and multiplication. We're then going to talk about signed numbers, and we're going to cover other forms of signed numbers besides the 2's complement that we spoke about earlier. Then we're going to talk about how to handle fractions. We're going to talk about fixed point numbers and floating point numbers. So before I get started, there's some readings from the book that I'm not going to cover. I'm not going to talk about division today. And you should go read this in the book. Remember, the reading assignments are on the website. And importantly, there's a signed reading for each of these lectures. Some of it covers stuff I've covered, and some of it has little details that I'm not going to cover. So when I tell you what's not in this lecture, don't take that to mean that this is the only thing you have to read. You really should read all the material that's listed in the book. So let's go ahead and get started with binary numbers. So why do computers use binary numbers? Well, basically because it's easy to build circuits. We can say 1 volt equals 1 and 0 volts equals 0. In the past, circuits used 3.3 or 5 volts or even 12 volts, but these days we keep pushing the voltage down to save energy. When you've got these two voltages, it's easy to build circuits with switches. We can switch 1s and 0s around to build useful functions, and those switches today are built out of transistors. So you could use multiple voltage levels. So you could build a circuit, for example, that used 1 volt for 1, 2 volts for 2, and 3 volts for 3. The problem with this is noise. And noise comes from all over the place. When circuits heat up or cool down, the transistors behave differently and you get different amounts of noise. If a circuit is brought near a radio, like a cell phone, that cell phone is going to cause noise in the circuits. So noise is a very big problem for designing circuits. Digital logic is particularly good because it's noise tolerant. So when you do an addition in digital logic, if you add a 1 and a 0, you'll get a 1. But if you have some noise on your inputs, so you have a 0.9 volts and 0.4 volts instead of 1 and 0, the circuit is going to interpret those still as a 1 and 0 and is going to output a 1. So the noise that goes into the circuit is not going to come out the other end. The circuit is going to regenerate just 1 and 0. Analog circuits don't do that. They carry their noise through. So if I want to add 1.4 and 3.4 volts, I'm going to get 4.8 volts. So if I was trying to add 1 and 3 and get 4, and the noise caused those to go up, my result is now closer to 5 than 4. So the noise is going through the circuits. So that's why we use binary numbers, but what's interesting about computer arithmetic is how we use those bits. So each number has a fixed number of bits, and there are a whole bunch of different ways we can interpret them. So now let's talk just about generally how you express numbers. So we have decimal numbers, and this is the standard way of expressing them. You have hundreds, tens, and ones places, which are 10 to the second, 10 to the first, 10. And you've got a decimal point. And then on the other side, you've got tenths, hundredths, and thousandth places. And you build up numbers by putting some digits to the left of this and some digits to the right. Everybody knows implicitly what the formula here is. We sum up all those digits times their place, and that gives us the number. So if we want to write 2.25, that's going to be 2 times 10 to the 0, plus 2 times 10 to the minus 1, plus 5 times 10 to the minus 2. Now decimal numbers are similar. So in binary, or base 2, we have the same sort of number line, but now we replace those 10 to the powers with 2 to the powers. And we still have this digit in the middle, this decimal point, but now it's a binary point. Here the formula is similar, except it's 2 times 2 to the i-th. Apologize for the mistake in the slide. If we want to write out the same number there, 2.25, it's now going to be 1 times 2 to the first, plus 0 times 2 to the second, plus 0 times 2 to the minus 1, plus 1 times 2 to the minus second, because 2 to the minus second is a quarter, and this will give us 2.25, or 10.01 in binary. So what are useful bases for computers? Why are we using binary? We talked about that being useful because it's easy to build circuits, but there are other ways to look at things as well. So base 10 in decimal, this isn't very good for computers, but it's great for humans because we all know how to read it. Base 2 binary, well, this isn't so great for humans, but it's great for computers because they can read it. And then there are two others that are often used. There's base 8 or octal. Here we have digits 0 through 7, so we have 8 digits. Or base 16, hexadecimal, which is often written 0x and then a number, which has 16 digits. So instead of in addition to the normal 0 through 9, we also have A, B, C, D, and E, and F, which represent the decimal numbers 10, 11, 12, up to 15. So here's a question. Why would we want to use octal or hex notation? What's the benefit of using either fewer numbers or more numbers when we write stuff out? Well, the answer here is that octal gives us exactly 3 bits per character. So we get 0 to 8, 0 to 7. Hex gives us 4 bits per character. We have 16 possible ones. So if we want to take a binary number and divide it up, dividing it up into 4 bits or 3 bits is really nice. Decimal numbers can take different numbers of bits depending on which number they are. So let's take a look at an example. Here we've got numbers in decimal, binary, and octal from 0 up to 14. And you can see the interesting one is hexadecimal here, which counts all the way up through 9 and then counts A, B, C, D, and E. When it continues, it goes on to F. So what you see from this is that if you look at the decimal numbers, so one decimal digit, 0 through 9, translates into somewhere between 1 and 4 binary digits. This is why it's not very convenient for expressing binary numbers in decimal. Whereas if you look at the hex and octal numbers, they're exactly 2 and 3 bits per digit. So that makes it much easier to use with computers. Another thing that's important to mention here when talking about bits are LSBs and MSBs. The LSB is the least significant bit, and MSB is the most significant bit. So if we have a number, here's the most significant bit, it's the largest place, it's on the left, and the least significant bit, it's the smallest place, or on the right. So I'm going to use these terms throughout the lecture, and you want to make sure you understand most significant bit, MSB is on the left, and least significant bit, LSB is on the right.